Hello, everyone, and welcome. My name is Dave Cunningham. I'm the Vice Chair of the Fiber Optic Sensing Association. I'd like to welcome you to the next webinar in our webinar series, and I'm going to hand it off right now to Mark Unkerfer to introduce our speaker and the topic.
Thank you very much, Dave, we're very pleased to have one of the active participants within FOSA's Technology Committee do a presentation today. Etienne Rochat is the Chief Technology Officer for Omnisens, and he's going to provide kind of a broad overview of the technology of how fiber optic sensing works. And so it's going to be a very, I think, useful presentation to understand the technology. Etienne, we look forward to hearing from you.
Thank you, Mark, for the kind introduction. And good morning, good afternoon, good evening. Very warm greeting from Switzerland, where I'm based. What I want to share with you today is a bit of the stories that we've seen in the field, the successes and also the progresses we are making by using Brillouin and Rayleigh fiber-based technology in the field, which we have done for the last 2 decades. So I will briefly say who we are, remind a little bit how distributed fiber optic sensing is working, and then we'll walk our way through offshore wind application, pipeline monitoring, structural health monitoring, and eventually I will bring a conclusion. Omnisens is a Swiss-based company, originally started from the Swiss Federal Institute of Technology in Lausanne, now a world leader in high-performance fiber optic monitoring, with a focus on the energy market and the transportation of energy. As I said, we've been in the field for more than 20 years, at least the company, myself a bit less than that. And we have solutions based today on the Brillouin, on Raman, and on Rayleigh. We are targeting pipeline monitoring, power cable monitoring, subsea, and we also targeting the test and measurement market, where we deliver solutions that are used in laboratory and for research purposes, and also things that I will quickly address today related to Geohazards and structural health monitoring. We approach monitoring as a solution. It means that there is somewhere in a set, a pipeline, a power cable, or whatever, on which we will have a sensor, which is a fiber optic cable, which is attached in the vicinity of the asset. We'll have an interrogator. We may have multiple interrogators in a large cabinet, and we are going to measure. So with those sensors, first we'll get some data, which we will process. We'll do alarm classification, we'll do alarm generation, we'll be looking for trends, for any meaningful information that can eventually be pushed to the end user. That's the monitoring part. And then the operator of the asset will have to manage the information and to take action. For instance, if we provide an information about a leak, then someone has to turn the pipeline off and then go on site to do something. Or if there is an alarm on ground movement, you have to decide whether you want to do any intervention in the field to stabilize the land and do something, or if you have third-party intrusion, then you have another set of action. And so eventually someone will act on the data which is coming from those sensors. We provide what we call dye test and orders, which are our name for the Brillouin-based temperature and strain monitoring system and the acoustic monitoring system featuring long distance capability. We have on top of that monitoring software that we brand as Lynx and Cobra for pipeline industry and power cable industry, and we have also dedicated application for Subsea Umbilical and Flowlines monitoring. And the solution is completely integrated. We begin with the discussion at the customer site at the very early stage of the project, and then we build up a full solution which is eventually connected to the end user SCADA and to the control room. We also look after the installation and the commissioning. We have field service engineers who are qualified to go onshore, offshore, have the certificate to do so. We have also the usual ISO certification, quality and safety management. Fiber optic monitoring is extremely powerful. I'm trying to have a little overview there, looking at temperature, DTS, at acoustic, and at strain, DSS. And if we concentrate first on the power cable application, well, with temperature, we can look at hotspots, which eventually may damage the cable or limit the load. We can do dynamic cable rating, basically computing dynamically the temperature of the conductor and then derive what can be done with the load. We can find fault. We can have information of depth of burial of the cable, mainly for subsea application. If we take acoustic monitoring, it provides access to faults, to cable impact, ankle drop, for instance. If we are on a terrestrial cable, we have access to third-party intrusion information, and if we are offshore, we may have access to fishing activities. And if we look at strain, we will get information like dynamic bending radius or tensile load on the cable, mainly during installation. That's something which will come in the near future. We have access to free span, to lateral dragging. Now, if we translate this to the pipeline world, temperature will provide leak detection or geohazard prevention, whilst DAS will provide third-party intrusion, and strain is more related also to geohazard prevention and the pipeline deformation itself. And if we go subsea with umbilical risers and subsea flowline, then there is again leak detection and electrical heat trace system monitoring, fault finding and depth of burial that we've seen before, likewise for the acoustic and for strain. So we see from that table that there are plenty of signal and signatures from the field that we can grab that can be used either to control, to operate the system, or to detect threat and eventually to take action. So how does it work? Well, we begin with a laser and a piece of fiber. We fire the laser in the fiber and we get some backscattering. That's the amount of light which is coming back to the emitter, which is tiny. And we can distinguish between three components on the way back. One is known as Rayleigh. It has the same wavelength than the initial laser, and it's used to evaluate the loss, transmission loss in the fiber, and also to look at the acoustic signal. And then we have an adjacent component which has almost the same wavelength. There's a little exchange of energy between the laser and the material, thus the shift in the frequency of the return signal. And Brillouin is essentially frequency sensitive to the temperature changes and the strain changes, which I've illustrated by this change in color. And then eventually we have the third and the smallest of all the scattering, which is Raman, which has a anti-stop component which is intensity sensitive to the temperature. And then whatever we do, we are playing with one or more of these backscattering signals. Now, when we put this in an instrument and we do a Brillouin-based DTS or DSS, the first thing we do is a time domain analysis. Essentially, we send a pulse of light down the fiber. We know the speed of light. We have a stopwatch to measure the time. And from that, we can compute the position of the emitted backscattering and therefore the position of the event, whatever the event is. That's the starting point. And then we do a frequency domain analysis. We get a raw data which looks a bit like the Alps or whatever mountain you want it to be, and we use calibration coefficient to extract from this value, for instance, the temperature. If we have a hotspot, then one of the summit will move away, and then again using the proper calibration coefficient, we can get the temperature value of this hotspot. And that is known as a BOTDR, a Brillouin optical time domain reflectometer. Single end, we send the pulse from one side and we get the feedback from the fiber. Now, the beauty of Brillouin is that the interaction can be stimulated by sending in the counter-propagating direction a signal that we call the probe. And the probe will make the interaction bigger, easier to measure. and eventually improve the performances. And we favor that BOTDA mode, the stimulated version, because we've seen that over distances that we are measuring, it's systematically the approach that provides the best performances. Now, something which is extremely important at this stage is to say that Brillouin, when it measures temperature or strain, is providing an absolute measurement. So we know it's 20 degree or 50 degree along the fiber. We know there is an elongation of 1% or 0, and that's completely absolute. And that is really fundamental for many applications. When we move to Rayleigh, well, we start again with the time domain analysis to get the position, and then we look at the backscattering signature, mainly looking at the intensity and its phase over the time. So we do a first measurement that we will call the reference, and then we do a second measurement, and we will evaluate the changes between the first and the second measurement, which I tried to illustrate by looking at the signal, which is constantly changing there. Rayleigh, like Brillouin, is sensitive to strain variation and temperature variation through the optical phase, but in this case, what we get is a relative measurement. So we don't know what the starting point is, but we know the changes from the starting point. And I'm insisting on this because regularly I see people claiming that they are doing temperature monitoring with DAS. No, you are doing at best a differential temperature monitoring or a delta temperature monitoring with the DAS, but you're measuring the temperature. And for some application, it's sufficient to have a variation, and for other application, it is absolutely mandatory to have the absolute value. There is also one point that I tend to insist more and more, that I used to dislike, but now that I understand what I can do with it, which I think is important, is the use of standards within the community. The standards basically are trying to bring definition that everybody can use in the same way. For instance, it explains how far we can go with the system. It explains how short we can measure, meaning how much detail can we get out of the fiber. And currently, for instance, there are interesting discussions about spatial resolution and gauge length, which are two definitions almost similar but not quite in the standard for that. How short. We have the how long, which is the measurement time, and obviously what everybody's interested in, which is the how well. For temperature, that is translated usually in the repeatability. For acoustic, it's more the dynamic range, the noise, and for a strain, it's the repeatability as well. I think the key points in the standard is that it brings a common language and common test methods, so that eventually when you compare performances, when you are looking at different instruments, that you can really compare things which are comparable. There are multiple groups involved in this. One at CFOM, people looking originally at subsea fiber monitoring. CFOM was the first to release two guidelines known as MSP01 and MSP02 for the DTS and DAS. There is a working group at IEC that came in, released one standard for DTS, one standard for DAS, and is about to release a standard on strain. There is a group at IEEE working on DAS, and at FOSA with the technology committee and the other people around, we are also trying to provide multiple guidelines and 1 pages on the FOSS technology to help everybody understand how it works, what we can do, what we can get out of that. Let's move now to the application, and first in the offshore wind, with something that I originally called reading the cable. It was a surprise to us. We had a cable which was about 88 kilometers long that at the time we instrumented with one instrument on each side, as shown here. We were looking at good repeatability with a measurement time of around 20 minutes, 5 meter spatial resolution. That's the setting that we agreed upon with the customer. And we got a trace which was going up and down all over the time with some jumps and then things which were smoother than others. and expectation was more or less that the trace would be flat for more or less everybody. And so we started looking in depth into those traces and could read much of the cable. One example is the depth of burial. We had at the beginning a few peaks there, and when we were looking at the sea depth and the position of the fiber, we could see that the sea bottom was going down and down and then up and down, and then the fiber was nicely, the cable was nicely following that, always with the same distance, apart from this position where obviously there was a quick difference in the depth of burial. It was a bit puzzling to see that when the seabed was a bit deeper, we had an increase in the temperature. But we realized later on, which seemed obvious when I say that, that there was a long time between the survey and the first measurement, and actually the seabed moved and became flat. And so instead of having a seabed going up and down, we had actually a flat seabed with the cable going down or going deeper into the seabed. And sure enough, if the cable is deeper in the North Sea, then you get a warmer cable, which explains the kind of signatures we had there. What is important to understand from this is that those hotspots could be limiting position along the cable route. If you ignore them, you may actually damage the cable, and if you know about them and you take them into account, they may force you to reduce the load eventually. So TTS was there to measure the temperature, but actually became a tool to understand what the seabed was doing. The offshore wind industry is pushing the wind farm further and further out. We have longer and longer export cables. So very early, we started looking at extending the sensing distance. I'm just sharing a few ideas and things that we did. The first and most straightforward, I assume, solution is to add an optical amplifier at the end of the loop on long distance, basically to handle the propagation of the probe signal. And by doing so, if you look at the optical budget, the loss of the fiber, and what is visible from the telecommunication industry, you realize that you can reach something which is around 250 kilometers, where each of the instruments is measuring about 125 kilometers also. The concept was first proven in the field already in 2017 with a 100 kilometer long cable. We are now finishing the commissioning of a 180 kilometer long cable with the same principle. I'll come back to that. What is really important there is that we don't have a dead zone in the middle section. We have a full coverage of the cable, and I think that is important. We used to say, well, some people used to say, if we don't know, we don't care. But as seen from the previous example, I think we need to know and we need to care about the cable and what is happening there. What we can also do in those situations is to do the measurement in two cycles. A first cycle concentrating with short spatial resolution over the first, let's say, 10 or 20 kilometers, potentially up to the HDD at the beach transition, or at the J-tube over the first 100 meters also from the offshore section. And then we do with longer spatial resolution and longer time measurement over the full cable, so that you can monitor the sensitive area and also get an information on the full cable. That's basically software configuration. If we want to push further, we can bring in distributed amplification, which is also a trick from the telecommunication industry, where on top of the Brillouin system, we combine a distributed Raman amplification. Essentially, it's a bit like making the first 30 kilometers of the fiber transparent in the system, and we can do this on both sides. If I look a little bit at the power distribution in a normal system, we would have our pumping signal, the pulse of light going down the fiber, which start at a certain level and then decrease over the distance simply by the attenuation of the fiber. And by the time you are around 120 kilometers or so, there is not enough energy there to trigger a signal that you can measure. When you bring in Raman amplification, what you do, in fact, is to push this position somewhere down the fiber by, let's say, about 30 kilometers, and that makes the range longer. That's for the pumping side. And if we look on the other side, so starting from, let's say, the probe side, which I put there, which has now to travel 250 kilometers. And then we have exactly the same concept to begin with. And then once the probe has traveled most of the fiber and is reaching that part of the gain, it goes up again and make sure that this section of the fiber, which is the most critical in terms of sensing, is nicely measured. This is a trick that we demonstrated already in 2014, then with 120 kilometers of fiber, and we had a hotspot, well, at 119.88, which was 5 meters long, which we put into a water bath, and you could clearly see the lab temperature and the hotspot temperature. And that opens the way, I think, to something like 150 kilometers, still in BOTD MEA mode. The only thing that you need to do is to have a passive loop in the cable, and that's something that has been done in the past already, and that we may have to do again on the very long interconnectors, and also maybe for the power from shore approach. So that was a bit theoretical, but it's working. And one example, which is based on also repeat technology, is the Crete-Peloponnese interconnector. So going from Crete, from the end of Greece to Crete, there is 135 kilometers of subsea route and a total of 180 kilometers of cable, which is measured from both sides. In fact, the architecture is more complex than that because there are more than one cable. But the principle is there, and to date is the longest interconnector which is fully measured with DTS. Some longer cable are being measured, but only for a few 20 kilometers on each side, which is not exactly the same. In that Crete-Peloponnese interconnector, we try to maintain short spatial resolution all the way to detect hotspot. We try to maintain short measurement times, so we really push the performances. And at the end of the day, 2/3 of the cable were measured with a repeatability of less than 0.5 degree, meaning that if you do the measurement again and again and again, you always get the same value. And it's only when you get to the middle of the cable that you start having a little bit wider repeatability. Eventually, when we made the test, which is shown in the figure, we had a total loop of total loss in the loop of about 37.4 dB on one way, which is slightly above 0.2 dB per kilometer, with 5 meter spatial resolution and 15 minutes measurement time. More recently, we've deployed DAS system on the Nemo-Link interconnector between Belgium and the UK. It's a massive HVDC 1 gigawatt 400 kV cable. The route is 140 kilometers long. The helix factor of the fiber inside the land section mainly and the offshore cable means that there is about 154 kilometers in fiber distance. That is a critical asset between the UK and Belgium, and the people, the user Nemo-Link, were looking at cable maintenance operation, at threat for the land section, fishing activities and vessel activities for the subsea, and also fault detection and localization. And to my knowledge, that's the longest interconnector which is fully measured with DAS as well. That's a few examples from the waterfall you can get on this thing. Very classical images where we see, for instance, some rock dumping activity there with the classical waves that we see most of the time. Some vessel crossing here, basically to illustrate the type of signature that we can get with the acoustic there. We have also been looking at dynamic strain and dynamic bending monitoring, the idea being that the installation of the cable is often the most critical part of its lifetime. It's where you may exceed the bending radius of the tensile load and damage it permanently. We first started looking at the deformation of those structures on oil and gas umbilical. It's a massive power cable that sometimes has also some hydraulic possibilities that maintain the communication from the platform to the seabed. And we worked in one of these systems by inserting in the carbon rod that makes the rigidity of the system. We inserted a cable, a 6 millimeter diameter, which featured a tight buffer fiber to measure strain and a loose tube fiber to measure the temperature. Idea, one of the possibilities of working with this during installation is to localize events, and then post-installation during the operation by looking at the DTS of the DAS signal is to look for deviation, and if there is any unexpected signature from the position where there was a measurement from excess strain or excess bending radius, then at least you can relate the issues you have with the installation. You can maybe mitigate or take measures in when to replace and how to do a repair job in a much better way than if you don't have that feedback. So that is a proven concept that was installed in the time, and I'm just showing here to illustrate the quality of the strain coupling that was achieved within those 3 positions. Well, we see that during the elongation test, they react very homogeneously, which was a very good point. And also during the bending test, here some data over a couple of days, we see something which is not noise, is in fact the movement of the system, the bending up and down on the strain, which is following inside the bend stiffener, which is under test. And if we look at the curves which is under here, it's outside the bend stiffener region. It's without any elongation, so it's kind of the strain cable being the reference. And you see that nothing is happening over time apart from the temperature changes as you would expect. I mentioned that we can do fault finding with those technologies. With DTS, we have access to unexpected hotspot, excess burial, free span, short circuit by activating the cable post-fault. With the DAS, we can have access to short circuit at the time of the fault, and also by post-activation. We have access to anchor drop. We have access also to the quality of cable protection system. I'll come back to these later on. I talked already about the DSS. I think using distributed fiber optic sensing for fault finding is about understanding what the fault is, identifying the reason of the fault, which helps mitigating it, and also provide an accurate localization along the cable, which ultimately is translated into fast access on site and shorter repair time. And there are some stories that you can hear or read here and there about the time it takes to repair a cable. And I'm convinced that if you can localize very quickly where the fault is, then you save a massive amount of time, and eventually your asset is back into production much faster. So a first example that we published a couple of years ago related to a fault that we found using a DTS. That's typically a cable where the company had been looking for the fault over months. Eventually decided to give it a go with the DTS. Fortunately, there was a fiber there, and sure enough, when they activated the fault, there was a clear hotspot, easily localized, and then with a little bit of fine-tuning and validation, they could go to the spot and do the repair. Localization in this case was within a week or so, because they went with a kind of habitat that they put around the cable in the water to do the repair. So you need to make sure that you are at the right position. Another example is a short circuit on power cable in a urban environment, where we see basically a short and unique and high amplitude signal from an acoustic point of view. Showing here the waterfall, and there is a clear difference from that type of signal with respect to the other that are related to the urban activities. I also mentioned that there is the possibility to look at cable protection system. Those CBS are fundamental to protect the cable when they exit the monopile inside the array. And it seems that there is currently a major challenge for the offshore wind industry as some CPS are moving across the scope protection area. There is some abrasion phenomena, and in some cases a failure. There is one developer that suggested something like a couple of hundreds of millions of euro cost for the replacement of the interarray cable due to those issues there. So far, the CPS are being surveyed by ROV, so go there with a camera and take a video or a few pictures, and you get a overview of the CPS status, which is a single shot view of the CPS. What we are trying to promote is that continuous monitoring method will give you information on trends potential, and you can then see that a CPS is being degraded or is getting worse, and therefore again plan when you want to replace it, and rather than having a possibly a failure over Christmas in the Rock Sea, you can maybe organize that for the summertime when everything is a bit smoother. Example of the waterfall in the interarray, where we again see waves. Obviously, that's always there. We also see the turbines, some of the turbines with the CPS, which are located on those sides. We are currently making a pilot test with the DAS located offshore in the North Sea. We are monitoring 4 strings in an interarray cable, looking specifically for the CPS, not only but mainly for this. We've been using machine learning based data processing and comparing the data with the survey, which are available. We were also looking at transferring the model from one string to the other, and we found a good agreement with the survey data, which is promising. When we were looking on a single string, the damaged CPS were correctly recognized, and some of them, which at the survey time were seen as good in that single shot view, seem actually to be not as good as expected. So it's a very valuable information. And when we look at the adjacent string and do a transfer of the model there, we also recognize correctly the damaged CPS with a little bit of dispersion in the intermediate case. So very promising, and we'll keep looking at this. Let's quit for some time the offshore wind and move to pipeline and discuss a little bit geotechnical monitoring. With the fiber system, mainly with strain and temperature, we have access to erosion. We have also access to subsidence and landslide. In the landslide, well, you have a certain distance which became under elongation that can develop very quickly. Because we have an absolute measurement, we can also compute a strain change, the slope, the speed at which it goes. And if we look at here, we see that the data were accumulated over 20 days or so. It's a very slow movement that we can grab at a very early stage and that we can follow and make sure that the people have time to get there. In this particular case, to begin with, there was nothing to be seen on the surface. So the land started moving under the surface, more or less at the level of the fiber, which allows us to grab and send a warning signal. Now, the interest in the absolute measurements is that you can follow those curves and you don't have to worry about any instrument stability or whatever, as you would do in a relative mode approach. If we look at subsidence, I'm sorry for the mathematics, but basically there is a position where the ground is stable, there is a position where the ground is under movement, and there is a transition zone, and we are going to measure the deformation of that fiber over the transition zone. And we did some in situ validation. Was a test place where people just dump massive amount of material, and sure enough, you see an increase in the strain along the fiber, and then you have some settlement, and it kind of decrease a little bit. And if you extract from the formula there the change delta H, so basically can change the vertical change of the soil, then you can also report that and see by how much it moved, in this case reaching almost 30 centimeter when it was fully loaded. Erosion is also important, for instance, along pipeline. In some cases, in the right of way, you start having one of these holes, and then water goes to the pipeline. You don't really want to have the pipeline in the water when it was not organized so. And usually it's quite easy to detect that, because you suddenly have a cold spot, which is related to the water coming in, and with a very narrow cold spot, so no natural extension. And also what quickly comes there is the fact that you see a daily temperature variation, so basically cold night and hot daytime. In a previous webinar, I also discussed how from this we can have access to aerial erosion, so the fact that the sand or the right of way is being swept away by wind. I won't come back to this today. I want to share a trial that we made on pipeline deformation a couple of years ago already, but interesting by the findings. So there was a pipeline that was instrumented with 3 fibers, 3 strain sensing fibers, 1 on the top, 1 on each side, plus in the trench, a different ground movement cable were installed. And so, because there was always the question of retrofit, the team there made 2 trenches in which they added ground movement sensing cable, and make a very unique trial comparing all those cables. We see here some of the termination on one of the cable attached to the pipeline, and hopefully you can see on the picture there a little red line which corresponds to one of the ground movement cable. Measurement was done with our BOTDA that we see here in its previous version. Now, what we expect from theory, if the land is moving on such a pipeline, is that some position will be under compression, others will be under elongation. And so if we look over the distance at the pattern, especially knowing that we have one fiber which is on the side from the landslide and the other which is on the other direction, so essentially they should see signals which are more or less symmetric. And so we predict to have large elongation and large compression for the fiber in the center of the deformation area, and then slightly smaller deformation elsewhere. And so the people started having the pipeline moving, and we see here basically those 2 fibers. And as it's moving over time, and sure enough, we see that shape with elongation, compression, and the symmetric information for the other one, where the position which is deformed is around 20 meters long. And if we look over time at the evolution of the different fibers, then we see the elongation and the compression for the fiber at 90 degrees and the one at 270, and also because excuse me, the direction of the movement is not aligned with the 2 fibers but is tilted, we are going to see some effect on the fiber on the top, as it is not anymore on the neutral axis of the deformation but slightly off that axis. And the results were compared with strain gauges, and we see that there is a very good map between the strain gauges and the fiber measurement. Then people also look at the ground movement cable in the trench and the ground movement cable in the retrofit trenches, so to speak. And you could see that for all of them, the soil deformation was well captured by the strain sensor and was a good indicator for the pipeline deformation, so good correlation between what's measured in the ground and what's measured on the pipe. And the same applied to the retrofit trench, and no significant delay between those positions. Also sharing a little bit about some subsea project on electric trace-heated pipeline. Essentially, the first one that we've been working on was Rayleigh, made together with technique for Total, where essentially you have an inner pipe with some electrical heating systems, some fibers for monitoring, thermal insulation, then you have an outer shell which protect everything before it's put into the water, thus the piping pipe design. And our scope at the time was to work on the cable and on the junction boxes that had to be put in there. The pipe was 6.2 kilometer in the North Sea, put into the water, operated for some time. That is an example of the temperature traces we got during the test phase. We see here the seabed, and when they installed the pipe, there was some water which remained in the pipe in those three lower places. And when you start testing and heating the system, sure enough, where there is the water, the temperature is not changing as quickly as in the other places, which makes those kind of dips, local dips in the temperature reading. In this case, there was a reading about every 45 seconds or so, and ultimately the operator managed to get those thermal information and put that into their model to optimize the system. More recently, with the same people, we've been working on the Fenia piping pipe, so basically the same structure, but a much longer one, now 37 kilometer, meaning more junction boxes, more losses, higher optical budget. So again, being measured with the Brillouin BTS, and again we looked after the cable and the junction boxes, and also took part to the installation. Had a number of crew looking after the project. I couldn't resist showing an extract of their video in that picture shape from one of my colleagues operating doing splices and splice protection in the junction box. So the cable itself is a central fiber in metal tube featuring 6 fibers, qualified for -40 to about 130 degrees C, and it has armor wires around there which are there to take over the load on the cable during the spooling, transportation, and the installation. There is also a dedicated junction box that goes in between the two pipes. That's what the colleague was doing, with a mechanism to lock the cable, and then the position in the center where we can handle the splice and the splice protection. Let's go shortly to structural health monitoring. One example is a tunnel in a mine, which is about 6 meters high and was instrumented with 4 fibers to look at the deformation. I'm not enough of a civil engineer myself to understand whether the results were good or bad or dangerous or safe, but what is sure is that over time we could see deformation of the tunnel due to whatever goes around it. Another example that we did with our partner Smartech is the monitoring of the Göteborg Bridge in Sweden. That bridge was built in 1939, about a kilometer long, used with heavy traffic to cross the river in the middle of the town. And about 15 years ago or so, multiple cracks were seen in some of the concrete section of the bridge, and unfortunately the new bridge wasn't ready, so the decision was taken to instrument that. And we supplied the interrogator, and for about 15 years has been measuring strain on those cable. The bridge is now being decommissioned. What was done there was to install about 5 kilometers of strain sensing cable. We see one of the crew there preparing the sensor and fixing it on the different position. We were looking essentially at cracks, so signals of deformation which normally are shorter than the spatial resolution of the instrument, typically 10 centimeters. But because Brillouin is a measurement in the spectral domain, if there is a crack, there will be in the spectrum a secondary peak. And so by having specific algorithms that are capable of following those cracks, those secondary peaks, it becomes possible to get an information on the cracks and the fact that they develop or they remain stable over time. I think it's about time to conclude. We've been working with Brillouin and Rayleigh for 2 decades in the field. It was fun and absolutely great. We have now proprietary technology for DTS, DSS, and DAS. In the offshore, we've seen that DTS can be used as a cable reading tool. It is also used more and more for real-time thermal rating and more depth of burial estimation. We have also seen that long-distance DTS and DAS are now possible, and with in the field 180 kilometer installed for the DTS and 154 for the DAS, measuring in both direction, and longer distance have been demonstrated in the lab also. DSS is still in progress. I think it's going to be a game changer in the future, providing dynamic acquisition and bending radius. We'll see how it goes. And when we use either DAS or DTS or combination of both, we have access to fault finding, cable protection system investigation also, so to the degradation of the set. Discussed a little bit pipeline geohazard with erosion, subsidence, and landslide monitoring. Obviously, with pipeline, there is also third-party intrusion and leak detection, but that will take another webinar. Subsea ETH pipe in pipe, where the DTS together with the dedicated cable and splice protection system has been used and put offshore successfully many times. Structural health monitoring with tunnel, bridges, dam, dike, and other that are being measured as well. I think what is important from those 2 decades, what we've learned is that you must match the right interrogator for the right application. The DTS, DSS, or DAS are not things that you can just change. You cannot pick one for the other. If you need to have an absolute measurement of the temperature, you cannot make a relative measurement, and vice versa. If you need to measure strain, don't use a DTS. So you have to select the most suitable technology for the application. Make sure you have the right one. Make sure you have also the right performances, because not all the DTS, not all the DAS are the same. So it's not only important to have the DTS or DAS, but it's also important to have one which provides the right performances. You have to understand the difference between absolute and relative measurement, and when necessary, you have to combine technologies, as we have seen during this talk. Full coverage is fundamental. You cannot just give away half of the cable. Well, unless it's 7 kilometers long, obviously, then it's getting difficult. And I think also that you need to have good data and therefore good instrumentation if you want to make good software application and computation on top of that. And with that, I thank you very much for your attention, and you have my contact details should you wish to contact me. Thank you.
Thank you very much, Etienne. It's a very informative presentation. We have quite a few questions, but let me kind of lead off with one. You've obviously demonstrated the waterfall pattern that detects events. Could you kind of elaborate on how a user can interpret that? How does that get turned into actionable information on the part of an actual user?
Well, I don't wish my customer to look at the waterfall all the time, because that's not really an easy and fascinating job. I think we show the waterfall because it's very representative of what is being done in the background. But in reality, you have software that are looking at components of that waterfall that are extracting information in different ways, and eventually will trigger an alarm so that someone can take an action. So if you happen to be there in front of the waterfall when something happens, it's nice, but essentially you have to understand that it's a 24/7 automatic processing system for those data. And that is not only true for the DAS and the waterfall, but it's also true for the DTS and the strain.
Sure. Now, the next question has to do with whether or not it's possible. You've obviously talked about the various flavors, temperature, acoustic, and strain. Is it possible to use these 3 methods all on the same fiber?
Being an optician, I would say in theory, yes. The telecommunication guys are multiplexing 100 wavelengths in the same fiber, and that's not an issue. Now, practically speaking, And given the fact that we have a lot of spare fiber in most of the cables that are being used in the industry, it probably doesn't make sense to do the combination into a single fiber. But in theory, that's known as wavelength division multiplexing.
And so I think in anticipation of that response, the follow-up question is what type of fiber is best for measuring temperature? Bare fibers, cable fibers, and this is in relationship to measurement error.
That is an interesting and challenging question. What we have access to, essentially, when measuring the temperature is the, let's put it this way, the temperature in the core of the fiber, where we have the interaction between the light and the glass, so to speak. Now, if you have a bare fiber, you have a very good measurement of the temperature in the sense that external temperature is directly grabbed by the fiber, because the fiber is small, is tiny, there is no mass to warm, there is no thermal delay or whatever. Now, working with a bare fiber is absolutely unpractical. We are talking about a quarter of a millimeter of glass and plastic, so there's nothing that you can do with this apart from the lab. It's not going to survive any installation. So as such, there isn't really a best fiber. You have cable design that are better than others because of their resistance to, I don't know, abrasion, to inside load, to crash, and things like this. Eventually, temperature will propagate everywhere, and as long as you have a cable which is small enough, let's say a couple of millimeters, the temperature that you will measure inside the cable is virtually the temperature that you have outside the cable. It's just that there is a little delay. So if you're looking at, let's say, a step function of the temperature increase very quickly, then in the fiber it will take a bit longer to reach that plateau. But apart from that, you will measure accurately the temperature in any cases.
So let me see if I can combine two questions. The first part is what is the wavelength of the test signal? And second part from another questioner is how does one distinguish between wavelengths difference to establish temperature-induced and strain-induced responses in the Brillouin system? Okay,
so essentially, when it comes to the wavelength, we are more or less all working around 1550 nanometers, simply because it's the position where the fiber is the most transparent, where the attenuation is the smallest, and therefore is where you can measure over the longest distance. But historically, other systems were, or previous system in the past, were working at completely different wavelengths, just because different fibers were available or different lasers were available. So that is for the wavelength. Now, when it comes to the split between strain and temperature in Brillouin, if I understand that this is the question.
Yes.
Yeah. So essentially, from the physics, there is a possibility to look at the frequency shift and the amplitude difference of the Brillouin spectrum, and if you can make kind of normalization on what the Brillouin gain should be locally, then you have an information where you can split temperature and strain. That's one way of doing it from the physics, basically. So either directly from the Brillouin signature, or in combination to what is known as the Landau-Plasek, where you basically Landau-Plasek coefficient, where you basically relate Rayleigh and Brillouin in terms of amplitude, and then you look at the local deviation of the Brillouin amplitude and the Brillouin frequency to extract the two components.
So we have another question.
There are other ways.
Sorry,
yeah,
go ahead.
Sorry, Mark. There are other ways to split between temperature and strain. I've been looking at this massively and realized that it's nice to do that from the physics, but when you look at the performances over long distance, you realize that it's not sufficient for the application, and it's much more efficient to work on the cable. In fact, the telecommunication guys and the people who are making fiber in metal tube, for instance, what they do best and they do all the time is to make sure that the fiber is strain-free. because the fiber under strain ultimately is a fiber which is going to break. So you try to protect the fiber, and by protecting the fiber, you decouple the strain, and that's an easy way to go, and it's a very efficient way of doing that.
So the next question is another optical fiber related question, and that is, what is the lowest temperature optical fiber in a metal tube can withstand?
Difficult to say. I'm not a filmed manufacturer. There has been tested at cryogenic temperature, so at least to probably liquid hydrogen or so. So I cannot point to a cable or cable data sheet directly, but surely to minus 170, minus 180 degree, there has been demonstration of temperature measurements using Brillouin, Rayleigh, and FINT that I'm aware of.
Okay, fair enough. And next is, what is the smallest leak that a system can detect in a product pipeline, both gas and liquid?
I don't have an answer to that. Within the TC in FOSA, we are trying to come up with some tables where we express all this. So let's wait for the work to be finished.
You are correct. We are working on that question. I thought maybe you'd get give you a preview opportunity there. Not for DAS. Well, do you analyze the acoustic spectrum to identify the signatures of different types of vibration source? So you can probably elaborate or clarify on that.
By looking at the spectrum and spectral content is one of the things that you can do in the DAS to analyze the data and to work out whether you have a relevant event or a threat or whatever. It's not the only one. There are more tools that you can use in the spectral domain or in the time domain. The waterfall being one of them. If you are looking at temperature differences, at strain differences in that relative mode, there's also things that you can extract directly from the raw data without going into the spectral domain. And I think in the DAS, what is important is that you get all the information from all the sources you have, and then you process that.
And this question is related to a specific slide, and this is on slide 27 for CPS. Can you explain what the DAS is looking at in slide 27?
Let me try to find 27. It's probably that one. What the DAS is looking at. On that waterfall, not much to be seen. The DAS essentially is looking for the behavior of the CPS and looking at the changes in behavior over time, and also of behavior between the different CPSs, and making comparison to extract that one CPS is potentially damaged and the other is not. But it takes a lot of processing from that waterfall figure to extract this.
Well, thank you. We've actually had quite a few questions asking for access to the presentation or for opportunities to share the presentation with others, and that is an easy question to answer, which is that this presentation will be available on the FOSA YouTube channel. And so folks can go through it and see it again and digest it, or also share it with their colleagues. And that usually is posted within, I would say a couple of hours after this. So you'll be able to go back through that. I'm afraid we're at the top of the hour, and there are some additional questions, but you do have your contact information, and so folks can ask you additional questions and reach out to you at your email address. And thank you very much. And that concludes this Fiber Optic Sensing Association webinar.